Hi everyone, my name is Syed Afir from the section D of AIML and my course is object-oriented programming and my given topic is robotics system. Today I am going to explain about it in a clear and brief manner. So I will start with defining the problem. So title of the problem project is robotics system and the defining the problem is design a robotics system capable for efficiently and safely navigating through a highly dynamic environment such as bustling warehouse, urban streets or crowded indoor spaces. The robot must handle unpredictable obstacles, moving entities, example people or other robots and environmental changes while achieving its goals. Challenges include real-time sensing and decision marketing. The system must use sensors, example LiDAR cameras, to pursue the environment and process data in real time to make navigation decision. And the second one is path planning in dynamic spaces. Develop algorithms that allow the robot to plan optimal paths while avoiding collisions with moving obstacles. And the third one is adaptable to environmental changes. The robot should adjust its behavior dynamically as the environment changes, such as moving through a warehouse during peak activity hours, multi-agent conditions. If operation alongside other robots, the system must coordinate to prevent conflicts, optimize routes, and ensure efficient task completion energy. And the fifth one is energy efficiency. Ensuring the robots completes navigation tasks without excessive power consumption, which is critical for mobile robots with limited battery life. This problem encapsulates real-world demands on robotics and provides a significant opportunities for innovation in algorithms, hardware, and software integration. Identifying strategies, perception and sensing, strategies, sensor functions. Combine data from multiple sensors, example cameras, LiDAR, ultrasonic sensors to create a comprehensive understanding of the environment. Simultaneous localization and mapping SLAM. Use sensors to build a map of the environment while simultaneously determining the robot's location within it. Deep learning for perception. Employ neural networks for object detection, recognition, and environmental classification. Next, navigation and mobility. Strategies, path planning algorithms. Use algorithms like A or Dijkstra for static environments and dynamic approaches, like rapidly exploring random trees, RTT for real-time adjustments. Obstacle avoidance. Implement reactive control methods, example, potential fields methods or predictive models to navigate around obstacles. Adaptive locomotion. Enable robots to adjust their movement styles, example, wheeled legged based on terrain conditions. Control and decision making strategies. Model predictive control, MPC. Optimize control inputs over a prediction horizon to achieve goals while maintaining stability. Behavior based control. Use hierarchical or subsumption architects where multiple behavior compete or cooperate to guide action. Reinforcement learning RL. Train robots to learn optimal actions based on rewards and penalties in various scenarios. Now, interaction and communication strategies. Human robot interaction HRI. Incorporate speech recognition, gestures, or visual cues for intuitive communication with humans, swarm intelligence. Use distributed algorithms to enable a group of robots to collaborate effectively without centralization and multiple agent coordination. Develop algorithms for task sharing and synchronization among multiple robots in a system. And the fifth one is energy efficiency and sustainable strategies. Energy aware scheduling. Prioritize tasks based on energy availability and recharge requirements. Renewable energy integration, use solar panels or other renewable sources to extend operational duration. Next, lightweight design. Optimize materials and design for reduce in energy consumption during movements. Next, learning and adaptation strategies. Transfer learning, apply knowledge learning in one context to improve performance in a new but related tasks. Continuous learning, enable robots to learn incrementally from their environment and adapt to changes. Fault tolerant learning, implement mechanism for detecting and correcting automatically. So here conclusion is the strategies ensure that robotics systems are efficient, robust, and versatile, addressing diverse applications like industrial automation, healthcare, logistics, and exploration. Strategies integration of these techniques is key to advancing robotic capabilities. Problem description challenges, dynamic and unpredictable environments, frequent movement of people, achieving inventory can lead to unforeseen obstacles. Next, unstructured data inputs. Items which are vary in shape, size, and arguments require flexible recognition system. Scalability. The system should be scalable to accommodate larger operations with increased throughput. And human robotic collaboration, ensuring safe interaction with the warehouse staff while maintaining productivity. Success matrix, reduction in material handling, time per task, improved accuracy in item identification and placements. Third one, decrease collision incidents or navigation errors. The fourth one, enhance system uptime and energy efficiency. The fifth one is seamless integration with existing warehouse systems. So here, sixth one is objectives. Automation of repetitive tasks. Reduce human intervention by automating routine and repetitive operations to enhance efficiency and precision. Example, industrial assembly lines, material handling and packaging. And from the second topic of objectives is precision and accuracy. Perform tasks with a high degree of accuracy, consistency, and minimal errors, surpassing human capabilities. Examples, surgical robots, semiconductor manufacturing, and precision welding. Adaptability to dynamic environments, respond and adapt to changes in the environment, such as moving obstacles or varying conditions in real time. Examples, autonomous vehicles such as rescue robots and warehouse robots, enhancing human productivity. Assist human by performing physically demanding hazardous or monotonous tasks, allowing them focus on highly level decision making. Examples, collaborative robots, cobots in factories, robotic exoskeletons for rehabilitation and teleoperation system. Cost reduction. Decrease operational costs through increased efficiency, reduced downtime, and lower resource consumption. Example, automated agriculture system and robotic process automation in businesses. Scalability and flexibility. Enable the system to scale up or down based on the scope of operations and adapt to different tasks or environments. Example, modular robots for manufacturing and multipurpose service robots. Seventh one, energy efficiency. Optimize energy use to maximize operational time and reduce the environmental footprint. Examples, solar powered exploration robots and energy aware industrial robots. The safety and reliability. Ensure safe operations in various environments, especially when interacting with humans or working in hazard areas. Examples, healthcare robots, bomb disposal robots, and autonomous drones. Ninth, advancing scientific and technical frontiers. Enable new discoveries or capabilities that are otherwise impossible or impractical humans. Examples, space exploration robots, underwater research robots, and robotics arms for practice physical experiments, enabling seamless human robot interaction, facilitate intuitive and effective communication between robots and humans to improve usability and collaboration. Example, service robots, home assistance robots, and interactive educational robots. And now, what are pre-requirements and requirements? And the first of all, pre-requirements, hardware requirements, sensors, perception and detection cameras, LiDAR, ultrasonic sensor, IR sensor, and proximity sensor for environmental awareness, position and orientation, GPS, IMUs, inertial measurement units, and echonders for navigation and localization, force and touch, tactile sensors for manipulation tasks or safe human interaction, actuators, motor servos, and hydraulic or pneumatic system to enable movement and manipulation. Power supply, batteries, solar panels, or wire powered sources tailored to the robot's energy consumption and mobility requirements. Processing units, microcontrollers, example, single board computers, Raspberry Pi, or powerful GPUs for real-time processing and decision making. Communication modules, Wi-Fi, Bluetooth, Zigbee, or cellular communication for remote operation and integration with other systems. Software requirements, control system, software to manage the robots, actuators, and movements based on sensors inputs, navigation algorithms, path planning, SLAM, simultaneous localization and mapping, and obstacle avoidance algorithm, machine learning AI, all AI models for object recognition, decision making, or learning from the environment. Operating system framework. Example, ROS robot operating system, VXOS, or custom firmware tailored to the robot's function. User interface. Interface for human robot interaction such as GUIs, voice commands, or remote control apps. And now interpretation findings. Interpreting finds for robotic systems. Interpreting finds in robotic systems involves analyzing data, performance metrics, and outcomes to derive meaningful conclusions. This process helps assess the system's effectiveness, identify potential improvements, and ensure alignment with project goals. Below are key areas to focus on when interpreting finds. First of all, performing matrix. Evaluate quantities matrix to assess how well the system meets its objectives. Example, accuracy, precision in the object recognition, navigation, or task execution, efficiency, time taken to complete tasks or optimize routes, real, reliability, consistency in performance across different scenarios or repeated trials, energy consumption, power usage, compared to task efficiency. Error and failure analysis. Identify pattern in errors or failures to determine underlying causes and areas for improvement. Example, navigation errors, deviation in the path planning or inability to avoid obstacles, mechanical failure, breakdown of ac- actuators or sensors due to design flaws or environmental factors, software bugs, inaccuracies in algorithm leading to incorrect decision. Behavior analysis. Assess how the robot behaves in different environment or under varying conditions. Key considerations. Adaptability. A system ability to handle dynamic changes like moving obstacles or lighting barriers. Robustness. Resilience to unexpected inputs or errors in real-time operations. Scalability. Compatibility to maintain perform as task complexity or operational scope increases. User feedback. Incorporate observations and input from operators, testers, or stakeholders. Questions to address. Was the system intuitive and easy to use? Did the robot enhance productively or require extensive human intervention? Where the safety concerns or discomfort in human robot interactions? And the data analysis. Analyze collected data from sensors, logs, or monitoring systems to uncover trends and insights. Techniques. Statistical analysis. Compare performance metrics across test cases. Visualization tools. Use graphs or heat maps to illustrate navigation paths, error zones, or operational efficiency. Machine learning insights. Train modes to predict or optimize future performance based on control data. And solving the problem solution development. Import java util.arrays. And from this head, this is called head of the code. And from this, we will develop code and we will execute and we will give the output. So let's get started.